Welcome back to the Deep Dive. Today we're diving straight into quantum computing. This field, it's not just evolving fast, it's really reshaping what we thought was even possible. Our mission, as always, is to guide you through a key source. This time it's latest advancements in quantum computers.pdf. We'll pull out the really important bits, the surprising facts, basically give you a shortcut to getting up to speed on this amazing topic.
Exactly. And it's important to say quantum computing isn't just theory anymore. The progress we're seeing now in R&D, it's really significant, a pivotal moment, actually.
Okay, let's unpack this then. What's the big picture the source paints? Where are the really exciting leaps happening right now?
Well, one truly groundbreaking area is what the source calls quantum supremacy milestones. And this isn't just like being a bit faster. We're talking about quantum computers solving problems that are fundamentally beyond what classical computers can even tackle.
Fundamentally beyond.
Yes, think of it as proving a whole new type of computation is real. It's a critical validation, showing this is becoming a practical, though, still early, technology.
That's a huge claim, solving problems classical computers cannot. Is there skepticism? How do we know it's not just clever optimization on their part? Can you give us a solid example, something concrete?
A perfect example. The source highlights is Google's Willow chip. That was a major step. So this chip performed a specific benchmark computation in, get this, under 5 minutes.
Okay. And for a classical computer?
That same task, it would take a top supercomputer, well, the estimate is billions of years, an incredibly long time, basically impossible.
Wow. Okay, that's not just faster.
Exactly. It's a qualitative difference.
Yeah.
And importantly, this achievement also showed real progress in quantum error correction. It strongly suggests that building much larger quantum computers is actually achievable because the Willow chip demonstrated, a significant reduction in errors as it got bigger, as it scaled up.
That Willow chip example really drives home the progress in, let's say, raw power. But making that power useful seems to hinge on something the source really digs into: qubit stability and error correction.
Right.
Why are these two concepts like the absolute linchpins here?
Right. The real challenge isn't just making qubits, it's making them stable enough to actually finish a complex calculation without, falling apart. Qubit instability. Imagine trying to solve a jigsaw puzzle on a table that's constantly vibrating.
Okay, I get that.
Qubits are incredibly fragile. They're super sensitive to noise, to their environment, which leads to error. So overcoming this fragility, this instability, it's like climbing Everest for quantum engineers. Every tiny error can cascade and mess up the whole calculation. This makes reliable, large-scale quantum computers impossible without really robust error correction. So yeah, improved qubit stability and error correction techniques, QEC, they are absolutely crucial.
So how are researchers trying to sort of tame these wild qubits? What are the specific strategies?
Well, one significant approach, the SOS details, comes from Microsoft. They're focusing heavily on something called topological qubits.
Topological, how does that work?
Think of it maybe like storing information in the pattern of a braid, rather than just on a single fragile thread. This structure makes them inherently more resistant to quantum decoherence.
Decoherence, that's when they lose their quantum state, right?
Exactly. When the environment basically makes the qubit forget its quantumness. So these topological qubits are expected to make error correction much more efficient, less complex than other qubit types. And Microsoft actually unveiled their Majorana 1 processor. It's a quantum processor powered by these topological qubits. It's a big proof point for this more stable architecture.
It's amazing to hear about these lab breakthroughs, but the big question is always, so what? What does this actually mean for, real-world uses? For making quantum computing something people can actually access?
You've hit the nail on the head. We are seeing real advancements in quantum algorithms. These are new types of algorithms designed specifically for quantum hardware, and they have potential in areas like cryptography, materials science, even machine learning, solving problems that are just intractable for classical computers today.
And it's not just algorithms, right? This source mentions commercial quantum cloud services are growing fast.
Yes, and that's huge for accessibility. Companies IBM, Google, Amazon, others are offering cloud platforms. These platforms give businesses, researchers, basically anyone access to their quantum processors. So you can explore applications without needing your own, multi-million-dollar quantum lab in the basement. It really lowers the barrier.
That cloud access model makes sense. But quantum computers are so specialized. Is the future really about replacing classical machines entirely? Or is it more maybe a team effort, combining quantum with what we already have?
The source definitely leans towards the latter. Quantum classical hybrid systems seem to be a very promising direction. It's about using the strengths of both. Classical computers do what they do best, and quantum processors tackle the parts of the problem they're uniquely suited for. It leads to more efficient problem solving overall. Think synergy, not replacement.
Okay, looking ahead. The source gives us a peek into trends for 2025 and beyond. What should we, the listeners, be watching for? What's coming down the pike in the near future?
Well, connecting back to what we discussed earlier, a major trend is the continued focus on logical qubits and error correction. We'll see more experiments aiming specifically to build fault-tolerant quantum computers. That's kind of the holy grail for reliable, widespread use.
Logical qubits. Can you explain that a bit more?
Sure, think of it like this. You take many physical qubits, which are inherently noisy and error-prone, and you bundle them together using clever error correction codes to create one highly reliable virtual qubit, a logical qubit. It's a bit like how RAID arrays use multiple physical hard drives to create one more reliable storage system in classical computing.
Ah, okay, that makes sense. Bundling for reliability. Now, you mentioned fault tolerance as the holy grail. Does the source suggest we're aiming for one giant universal quantum computer? Or is a different strategy maybe emerging?
That's a really good question. And actually, there's a noticeable shift towards specialized hardware and software. Instead of maybe waiting decades for a perfect universal machine, developers are increasingly building specialized quantum hardware and software, tailored for specific types of problems like drug simulation or materials science. It's a pragmatic approach, aiming to get commercial value and solve real problems sooner.
What about linking these machines? Is a quantum internet, connecting quantum computers still just sci-fi?
Well, it's not here yet, but quantum networking efforts are definitely making real progress. It's paving the way. Researchers are demonstrating things like distributed entanglement.
Entanglement between different machines.
Yes, creating those unique quantum links between qubits in machines that might be miles apart. That's a foundational step if you ever want to build something like a quantum internet. So progress, yes. Sci-fi. Moving away from it.
And for the people who want to actually use these machines, the developers,
Yeah.
how's accessibility improving beyond just hardware?
There's a big push for networking and software abstraction. Part of this involves linking up today's machines, the NISQ devices, that's noisy intermediate scale quantum. They're powerful but still error-prone. The goal is to make them work together better, but also to build more layers of software abstraction, basically making it easier for people to program and use quantum computers without needing to be, deep quantum physicists.
That makes sense. You need the tools. What about the people, though, the human side? The source mentions workforce development. How critical is that?
Oh, it's absolutely vital. There's a huge demand for people with quantum skills, which are pretty specialized. So we're seeing a big push in universities, industry training, certifications. You need people who can build, operate, and crucially innovate with these machines.
And are we still seeing improvements at the most basic level, like the physical qubits themselves, advancements in physical qubits?
Oh, definitely. That foundational research hasn't stopped. Scientists are constantly working to improve the qubits themselves, longer coherence times, meaning they stay quantum for longer, better connectivity between qubits. All of that is crucial for scaling up and building better machines in the future.
Okay, it sounds incredibly promising, almost like science fiction becoming reality,
Yeah.
step by step. But the source is also realistic. It outlines some pretty major challenges. What are the biggest hurdles still in the way?
Yeah, despite all the progress, quantum error correction, QEC, it remains a really significant challenge. Getting QEC to the level needed for truly fault-tolerant computing, that's still a huge mountain to climb. Just isolating these incredibly sensitive systems from any environmental noise is immensely difficult.
And beyond the error correction logic, physically building these things must be a nightmare, right? Getting them out of pristine labs.
That's absolutely spot on. Hardware construction is another massive hurdle. We're talking about building hardware that's not just scalable, but also robust. Hardware that can actually work reliably outside these ultra-controlled lab environments. Labs with extreme cooling, perfect vibration isolation. Translating that to something more practical is a major engineering feat.
And then there's a challenge that affects, well, potentially everyone, a big societal one the source raises.
Yes, and this is something we all need to be aware of, the quantum threat to cryptography. The scary part is that a powerful enough quantum computer could potentially break many of the encryption methods we rely on today.
Like for banking, secure communications, everything.
Pretty much everything secured by current standards, yes. This creates a really urgent need to develop and, importantly, adopt quantum-resistant cryptography. New encryption methods safe from quantum attacks. It's genuinely a race against time to upgrade our digital infrastructure before the threat becomes real.
So wrapping this up, if we distill everything we've talked about from the source, quantum computing is clearly evolving at, well, a blistering pace. Huge progress, especially with error correction, qubit counts.
Exactly. And while, yes, there are still substantial challenges, big ones, the advancements really do point towards a future where quantum computing plays a major role across many different industries, fundamentally changing how we tackle the world's hardest problems.
So here's something for you, our listener, to think about. Considering all this progress and the hurdles still ahead, what industries do you believe will be most profoundly transformed by quantum computing in, say, the next 10 years? And what might that transformation actually mean for our collective future? Something to ponder.